I'll go a little fast considering that we have already done this. But please, barbar abar kore ami bolchi, if you have any doubt anywhere, do stop me and ask me to repeat or ask me question related to that. Okay, so what we are going to do is this is
ম্যাম
হ্যাঁ বলো।
ম্যাম আপনি আরেকবার বলবেন, আমি তখন এটা শুনতে পেলাম না। আমরা মানে কোনটায় মানে কিসে যেটা অ্যাটেম্প করি সেটা একটু আন্ডারস্ট্যান্ডিং এ কম আছে, মানে জাস্ট ওই পার্টটা।
এই যেটা এখন বলবো বাউন্ড স্টেটস,
মানে বাউন্ড স্টেট। আচ্ছা ঠিক আছে।
Bound states is very important because this is the first place where quantization, discrete quantum levels arise. So although the mathematics of bound states is not very difficult, in fact free states এ যে mathematics টা আমরা করি সেটা অনেক বেশি involved, a lot of mathematics, lot of trigonometry, lot of calculations and algebra, long derivations. Even when we do harmonic oscillator and hydrogen atom, you will see there are a lot of long derivations. Bound state e seta nei, kintu the fact that energy quantization, appearance of discrete levels, appearance of different modes of the wave function are encountered for the first time here. That is why the understanding of this problem is very important. Clear understanding of this problem is very important. Okay, so I was pretty surprised because this was a pretty straightforward question that I had given. First of all, very few people attempted it. Those who attempted it, since the mathematics was right, কারণ mathematics টা তো কপি করে লিখেছে, ওখানে তো ভুল হওয়ার জায়গা নেই, which is why they probably got marks সবাইকে দিয়েছি আমি। কিন্তু the way the thing was written, the steps followed, the physics part কোথাও ছিল না, which is why I felt যে there is some shortage in understanding, and most importantly হচ্ছে zero point energy. Zero point energy এত খারাপ খারাপ definition আমি পেয়েছি, যেটা আমি আগের দিনও বলছিলাম যে it was really disheartening. Because anyway, I'll do the whole thing again so you'll get to know. So we have gone extensively through the applications of Schrodinger equation, and we know that there are two kinds of states. First of all is free state and in free state, and the other part is bound state. Okay, so in free state we did the free particle, the step potential, the potential barrier, etc. And in the bound state we are going to encounter the one-dimensional infinitely rigid potential box. And the three-dimensional potential box is not mentioned in the syllabus, but studying or discussing the bound state without mentioning the 3D potential box is not justified, which is why I will just mention this, the 3D potential box. Okay, now what are bound states? Of course the word bound is there, which means that the particle is no longer free. Okay, so like in step potential or in potential wall or barrier, we saw that the particle is approaching from a potential free region, and then it has a wall or a barrier of a finite height in front of it, right? So then the particle then acts in a certain way when it encounters that wall or step. In bound state, the particle is not approaching from a potential free region. It is confined to a region, which is confined within a region from which it cannot come out. Okay, this is the first difference between a bound state and a free state. It is not coming, it is not approaching or going anywhere. It is confined within a region from which it cannot come out. Okay, so the box or the well in which the particle is confined, from the name, you know, the box or the well, যদি well কথাটা ভাবো, কুঁয়ো যেটাকে আমরা বাংলায় বলি, the particle is trapped inside a well, an infinite potential well. So where the walls are of infinite potential and the walls are impenetrable. Okay, so that is the boundary within which the particle is trapped. All right, so this is the problem that we are going to encounter, and this is the problem that we are going to address. All right, now তোমাদের মনে হতে পারে যে এই যে ম্যাথমেটিক্যালি আমরা যে প্রবলেমটা করতে চলেছি এটার প্র্যাকটিক্যাল রিয়েলাইজেশন কি? How do we realize a practical situation where a particle is trapped like this within an infinite well, where the walls are impenetrable and the walls are infinitely high? High not in terms of height, remember, high in terms of potential, okay, which is why the particle cannot overcome that, but the particle cannot gather energy enough to overcome that high potential and go outside the boundary. So the simplest example of this kind of a problem is the deuteron atom, okay, the deuteron nucleus rather. So in the deuteron nucleus, deuteron মানে সবাই জানো heavy hydrogen যেটা, deuteron, inside the deuteron nucleus there are two nucleons which are bound by the strong nuclear forces, that also you know. Now in nature deuteron is a very unstable nucleus, okay, it is barely, the nucleons are barely bound, okay, and they do not have any excited state. So the square well that we approximate in this problem is very much like the potential that the nucleons face inside the nucleus of a deuteron, and if you apply this, then the results that are obtained match very well with the experimentally obtained observations involving deuteron, okay. Like the if you consider the nuclear force in which the nucleons are there in deuteron, the value of the well is 35 mega electron volt, okay, which is a very very high value, whereas the ground state is a very low 2.2 mega electron volt. So 2.2 or 35 and 35 mega electron volt is like an infinite wall in front of a 2.2 mega electron volt. All right. So which is why the particle is bound, is trapped inside the well. Another example হচ্ছে metal say electrons inside a metal. They can also be conceived as particles in a box. So these are practical examples where you can get a situation where a particle can be considered to be trapped inside a infinitely high potential well with impenetrable walls, okay. So when we studied free particle states, we encountered things like penetration. If you remember that the wall is impenetrable, particle is coming with an energy less than the potential of the wall, but still there is some penetration, which is a quantum phenomena. We saw tunneling, which is widely used in tunnel diode. We saw how alpha decay takes place using this concept, okay. So penetration and tunneling into the classically forbidden region is possible only if you apply quantum mechanics. It is experimentally observed, not explained using classical physics. You apply Schrodinger equation, apply quantum mechanics, and you can explain how tunneling and penetration takes place. Now let's see what happens when a particle is bound within a potential well. All right. So the first problem, and the only problem in fact, is the one-dimensional infinitely rigid potential box. You can also call it a potential well since it is a one-dimensional case. So this is the scenario. All right. You have along, so this is the x-axis along which the particle is moving, and along the y-axis you have the walls of the well or the box, 1D box. These walls are infinitely high, so the potential at the walls is infinite, and the potential within the box is 0. Okay. Obviously, this is an ideal case. Puro infinite or puro 0 hoy na, but compare it. If you compare the two, then the potential of the walls is so high relative to the potential inside the box that you can consider them to be 0 and infinite. All right. So this is where the particle is trapped inside this potential free region. Okay. So walls of the box are situated at x equal to 0 and x equal to L. Some books take the mathematics in the form as x equal to L by 2 and minus L by 2 and plus L by 2. That you can also do. There is no problem with that. Just remember that the walls are present either at minus L by 2 and plus L by 2 or at 0 at L. The result that you will get will be the same in both the cases. So potential is 0 if x is less than 0, sorry, greater than 0, less than L, and potential is infinite if x is less than 0 and x is greater than L. The picture says it all, so it's self-explanatory, I guess. Now, certain assumptions are there. First of all, particle which is inside in this free region, if it moves towards the x direction, it will face the wall, it will collide with the wall, and it will be made to change its direction, and then it will collide with the other wall. Okay, so it will of course collide with the walls. Now we assume that these collisions are elastic. Okay, just to keep the problem simple, you can of course ask that is the collision really elastic? I don't know. Maybe they are not all elastic, but to keep the problem simple and yet to keep the problem simple and yet get the results that are experimentally obtained, we keep the assumption that the collisions with the wall are elastic, which means that there is no change in energy of the particle when it collides with the walls. Otherwise, there may be a change in the energy. Okay. Now, question is, can the particle leave the box? আমরা আগে দেখেছি যে particle is approaching with an energy lesser than the energy of the step or the wall, and yet the particle can, penetrate and so on. In this case, can the particle leave the box? It can only if it performs infinite amount of work. Okay, so the particle in this case is trapped inside the infinitely high potential wall, and so it can leave the box only if it can perform an infinite amount of work, which is not possible. We all know that because of thermodynamics, infinite amount of work cannot be performed, which means that particle cannot exist outside the boundaries of the box. At any instant of time, we may get the particle only inside the box. We cannot get the particle outside the boundaries of the box. Please don't unmute if you don't have a question. So, picture is very clear now. It keeps bouncing back and forth between the walls. It's almost like one of those video games that we used to play. আমি জানি না তোমরা কেউ খেলেছো কিনা, আমরা খেলতাম. There are several balls within a wall, within a well, and the balls keep bouncing back and forth, and then we have to eliminate the balls one by one. So that's the way the particle is behaving inside the box. It just keeps moving, bouncing back and forth. Now, this is a very well studied classical problem. If you have done some mechanics in your high school, the problem of conservation of momentum and energy, then you have all done this problem where a particle keeps moving back and forth between the walls of a chamber, and we see that if the collision is, this was done in the chapter of collisions, okay, where you study elastic and non-elastic collisions. So if the particle is performing elastic collision with the walls. Then you apply conservation of momentum and conservation of energy, and you'll see that the particle will have constant momentum, that is constant magnitude, but varying direction, because every time it collides, its direction changes. So magnitude of the momentum doesn't change, but the direction keeps changing. And energy can have any value. There is no restriction on the value of the energy that the particle might have when it is bouncing back and forth between the walls of the infinite potential well. This is the classical result. Okay. However, if you treat this problem using Schrodinger equation, that is, if you treat this problem quantum mechanically, then we get results which are very, very different from the results that we get classically. Okay. So since the particle cannot exist outside the box, we can start our solution by writing down that psi x equal to 0 for mod x greater than L. Psi x does not exist outside the well. Inside the well, there is no potential, so V is 0. So time independent Schrodinger equation, by now you should all be able to write it down before me and better than me. So inside the wall, this is the Schrodinger equation that you will write down. Solve it. We have solved it many times for the free particle. This is the free particle Schrodinger equation. So this is the final form, where kappa is root over 2m e by h cut square, E being the total energy of the particle. And at once we can write down the solution psi x equal to a sin kappa x plus b cos kappa x, right? This is the solution that we get. This much is like very easy because you have done this so many times in your earlier quantum mechanics problems. Now the main difference from the other problems, from the earlier problems, comes in here, because now we are going to apply the boundary conditions to find out the values of A and B. A and B are constants of integration. So now we are going to apply the boundary conditions. And in applying the boundary conditions, we know that we have to keep in mind that the function should be well behaved, correct? The function should be well behaved. So it should be continuous at the boundaries, and its derivative should also be continuous at the boundaries. Okay. Okay. Boundary condition: psi x equal to 0 at x equal to 0, psi x equal to 0 at x equal to L. Why? Because function should be continuous at the boundaries. Function is 0 outside x equal to 0 and x equal to L. So at x equal to 0 and x equal to L, to maintain the condition of continuity, the function should also be 0. Correct? So you put this in the expression of psi x, and you get a into 0 plus b into 0 equal to plus b equal to 0, which means b is 0. So at once one constant goes, so you are left with psi x equal to a sin kappa x, and then at x equal to a again, x equal to L again the function is 0, so a sin kappa a equal to 0. এখানে একটু ওই a আর L টা একটু কনফিউশন আছে, হ্যাঁ, এটা x equal to a করলেও হতো, তাহলে এটা x equal to a, মানে a and L are the same things. Please don't get confused. Now this is possible either if the constant of integration capital A is 0, or if sin kappa equal to 0. If capital A becomes 0, then the function becomes identically 0, which cannot be the case because the function does exist inside the well. So capital A not equal to 0. So we have sin kappa L equal to 0. Okay. Now sin kappa L equal to 0 only if kappa L equal to n pi, n being an integer. Therefore, kappa equal to n pi by L, L being the length of the box. Remember, n is an integer but non-zero, because if n becomes 0, then again we will get a null result. That is, again psi will become 0, which cannot be the case because we are dealing with a particle inside the box. So the wave function must exist. So the solutions are possible only if n be a non-zero integer. All right. So this is the solution that we get for kappa. So we quickly write down the form of psi x. Only now we add a suffix n, because you can see that the function is a sine n pi x by L. We write n pi by L in place of kappa. And since n can take different values, we attach a suffix n with the wave function. All right. Clearly, these are the eigenfunctions of the particle, because these satisfy the eigenvalue equation, which means that these are the eigenfunctions of the particle. Now, from the expression of kappa, which is root over 2me by h cut square, if you equate it with n pi by L, then you get the energy values to be n square pi square h cut square by 2ml square. Once again, n can take values 1, 2, 3, etc., which is why the energy values will also change depending on the value of n. All right. So we also attach a suffix n to the energy. Clear? And again, clearly, these are the energy eigenvalues of the particle. So we get the eigenfunctions of the particle psi nx, and we get the energy eigenvalues of the particle En in terms of known constants m and capital L, mass of the particle and length of the potential box. So this is the eigenvalue equation followed by the wave function, of course, h psi n equal to En psi n. This n is called the quantum number corresponding to the eigenvalue En for an eigenfunction psi nx. Why it is called the quantum number? You'll get to know in a moment. For the time being, just see that this integer that comes up for solving for the function psi in this particular problem using the continuity of the wave function at the boundaries, this number n plays a very, very significant role in deciding the nature of the solution. It is because of the appearance of this number n, the non-zero integer, that the wave functions are of this form and the energy values are of this form. The only deciding, L is a constant, M is a constant. So the only deciding factor of the function and the different values of energy is n. N is a very, very significant number. It is called the quantum number. For a given quantum number n, we get a particular energy En and a particular eigenfunction psi nx. Is this part clear to everybody? Have you realized the importance of n? এখানটা যদি clear না থাকে তাহলে please আমাকে একবার বলো, আমি আরেকবার explain করব। কিন্তু the important understanding the importance of n, the quantum number, is very, very important. কি করে n টা আসছে এবং কি significance ওই n টা, understanding that is very important. এখানটা যদি অসুবিধা থাকে আমাকে বলো, আমি আরেকবার repeat করব, আর না হলে I'll go to the next slide. Should I continue?
Yes, ma'am.
Okay. Okay. So for a হ্যাঁ বলো।
ম্যাম বলছি মেটালে যে ফ্রি ইলেকট্রন গুলো আছে ওগুলোর ক্ষেত্রে কি বাউন্ড প্রবলেমটা কাজ করবে?
হ্যাঁ, মেটালের কন্ডাকশন ব্যান্ডে যে ফ্রি ইলেকট্রন গুলো আছে ওখানে এই ওরা এইটা ফলো করে আর কি, মানে ওদের ক্ষেত্রে তুমি এই পোটেনশিয়াল ওয়েল, ইনফাইনাইট পোটেনশিয়াল ওয়েল প্রবলেমটা তুমি কাজে লাগাতে পারো মেটালের কন্ডাকশন ব্যান্ডে যে ফ্রি ইলেকট্রন গুলো আছে।
ঠিক আছে।
Okay, so for a given integer n non-zero, we get a particular state and a particular value of energy. All right, now we'll note some important points regarding this. You see, since n is non-zero, the minimum possible value of the energy En is for n equal to 1. Because n equal to 1 is the lowest value of n. So the minimum possible value of energy is En, which comes for n equal to 1, which is non-zero, right? So a particle cannot have zero energy. It cannot stay at rest. It has to have some amount of energy, which is clear from the expression. And this lowest energy is given by E1 equal to pi square h cut square by 2 ml square for n equal to 1. Okay, this is the ground state energy of the particle. This is the lowest possible energy of the particle, and this is called the ground state energy of the particle. Okay, for n equal to 2, we get a higher energy E2, which we can clearly see that it is 2 squared times E1. So it is a multiple of E1, the ground state. For n equal to 3, it is 3 squared E1. So again a multiple of the ground state energy. And in this manner, for a given nth value of the integer n, we get the energy En as n squared E1. So n squared times the ground state energy. So for any given n, the energy for that particular state is n squared times the ground state energy, that is the minimum energy that the particle can have. So starting from n equal to 2, as we move higher on, these are all the higher excited states. So the lowest value is called the ground state, and all the higher values are called the higher excited states. So the particle will try to be in the ground state, but if it gets some energy from outside, it might go to a higher excited states. But as you can see that it cannot have any value in between two states. It cannot have a value which might be given by a value of n between 2 and 3. It can either have a value for n equal to 2 or n equal to 3, but nothing in between n equal to 2 and 3. So this is very important, that n has integral values only, and these values that I have written down here are the only possible values of energy. Okay, so whatever energy you give the particle from outside to whichever higher excited state it may get, it may go, it can have only these possible values. It cannot be in between these values. Okay, so energy cannot have any possible values. Energy cannot be continuous. It can have only certain discrete values. Cannot be continuous. So we have now got discrete energy levels decided by the values of the quantum number n. The values of the energy levels are decided by the quantum number n. So once again you realize the importance of the appearance of n in this problem. First time we are encountering quantization of energy. This is why I told you that we'll soon get to see why n is called the quantum number. Because the first time we get to see quantization of energy, we have a fixed ground state energy decided by the system parameters m and l, and then all the higher state energies are just multiples of that ground state energy. And what multiple? The multiple is decided by this quantum number n, by this integer n that comes out from the solution of the Schrodinger equation under the given condition. Okay, so please try to think very logically. Puro ব্যাপারটা কিন্তু খুব logical. It's almost like an algorithm. Okay, লজিকের বাইরে কিচ্ছু নেই, মানে এটা একটু সিকোয়েন্সিয়ালি এটা একটু ভাবার আছে, মানে ইনস্টেড অফ জাস্ট লার্নিং আপ, মুখস্থ করাটা তো খুব সহজ, কারণ অঙ্কটা খুব সহজ, কিন্তু ইনস্টেড অফ লার্নিং বাই রোট, ট্রাই টু থিঙ্ক the entire problem as a logical sequence. Okay, and I'll give you the sequence that you have to think about. Particle trapped in a region where there is no potential, but the boundaries of this trap have infinite potential, so the particle cannot go outside. So psi x, the function representing the particle, has a value inside the well, is 0 outside the well. এটা হচ্ছে ফার্স্ট অ্যালগরিদমের ফার্স্ট স্টেপ। নেক্সট, ইনসাইড দ্য ওয়েল ফ্রি পার্টিকেল, নো পোটেনশিয়াল, সঙ্গে সঙ্গে শর্টেনজের ইকুয়েশন সলভ করে ফেলো, পেলে সলিউশন a sin kx plus b sin kx. How do you get the constants of integration a and b? You apply boundary condition. How do you apply boundary condition? From the fact that the particle should be well behaved. What is the first criteria of being well behaved? The particle should be, the wave function should be continuous at the boundaries. So to be continuous at the boundaries, since it is 0 outside and finite inside, so at the boundaries it should be 0. Apply that, you get the solution to be a sin kappa x for x equal to 0. Next boundary, x equal to a, shekhaneo 0, x equal to l, shekhaneo 0. Possible only if kappa is equal to n pi by l. The moment you get kappa as n pi by l, you put it in the expression of kappa which you had substituted as root over 2me by h cut square. You get the values of energy to be discrete, dependent on n. You get n which are only non-zero integers, and therefore you get only particular values of psi for a given n. So psi n for different non-zero values of n given by a sin n pi x by l, and energy given by n square pi square h cut square by 2ml. Okay, is the মানে সিকোয়েন্সটা ক্লিয়ার হয়েছে কি সবার, কিভাবে এই কোয়ান্টাইজেশনে অ্যারাইভ করছি? Is it clear to everybody?
Yes, ma'am.
Okay, মানে যখন নিজেরা পড়বে এই জিনিসটা কিন্তু পড়বে, হ্যাঁ, এই জিনিসটা বাদ দিয়ে যাবে না। মানে তোমাদের এখন সিচুয়েশনটা তো ওপেন বুক টেস্ট, বই দেখে লিখতে পারছো, সবই বুঝলাম, কিন্তু মানে ফিজিক্সটা তোমরা অনার্স পড়তে এসছো, সাবজেক্টটা তো মানে আমি পরীক্ষা বই দেখে দিয়ে ফেলেছি, নম্বর পেয়ে গেছি, তোমরা তো মানে আমার মতে আর কি শুধু নম্বর পেতে তো আসোনি, ফিজিক্স সাবজেক্টটাও তো ইটস আ ভেরি বিউটিফুল সাবজেক্ট, সেটা তো জানাও দরকার। মানে সো ইউ নিড টু কিপ দ্য লজিক্যাল সিকোয়েন্সেস ভেরি ক্লিয়ার ইন ইউর হেড। মুখস্থ করবে না, এই যে আমি সিকোয়েন্সটা বললাম, এটা লজিক্যালি তুমিও যদি বসে এই লজিক্যালি ভাবো এই সিকোয়েন্সটা, তাহলে তোমাকে আর কোনোদিন মুখস্থ করতেই হবে না। কোয়ান্টাইজেশন অফ এনার্জি কিভাবে অ্যারাইজ করছে 1D পোটেনশিয়াল ওয়েলের ক্ষেত্রে তোমাকে কোনোদিন মুখস্থ করতেই হবে না, শুধু এই সিকোয়েন্সটা মনে রাখলেই তোমার হয়ে যাবে। যখন পড়বে নিজে তখন ঠিক এইভাবেই পড়বে, তাহলে আর মুখস্থ করার কোনো দরকার নেই। মুখস্থ যদি না করতে হয় তাহলে ভুল হওয়ারও কোনো চান্স নেই। আমরা লিখতে বসে ভুল করি, তার কারণ আমরা মুখস্থ করি, এবং মুখস্থ করতে গিয়ে যে জায়গাগুলো মিস হয়ে যায় সেগুলোই লিখতে গিয়ে আমরা ভুলে যাই, তখনই আমাদের ভুল হয়। তুমি যদি মুখস্থ না করো, তুমি যদি লজিক্যালি ভেবে একটা জিনিস পড়ো, তাহলে কিন্তু সেইটার আর কোনো চান্স নেই। ঠিক আছে? So the first time we are encountering quantization of energy. So you see that there are only certain allowed energy levels, and you can very easily calculate the gap between any two consecutive allowed energy levels. So if the first if one allowed energy level is En and the next allowed energy level is En plus 1, then you take the difference between the two. It's only a matter of n. N is the only governing factor because any energy level is n squared times the ground state. So it is n plus 1 square minus n square times the ground state energy. So it is 2n plus 1 E1. So clearly, as you go to higher values of n, the gap between consecutive energy levels will increase because E1 remains the same. For a given system, E1 remains the same. So as you go to higher values of n, the gap between two consecutive levels will increase. So higher energy levels are more widely spaced. This is the energy level diagram. Okay, see the zero stage does not have a level because there is no zero energy. The first level, that is the ground state, appears at n equal to 1, then at n equal to 2, then at n equal to 3 and so on. And as you move higher up the energy ladder, the gap becomes wider. Okay, so this is the energy level diagram that arises for the one-dimensional potential, infinite potential wall within which a particle is trapped in a potential free region. Okay, now next, the things that come are all mathematical aspects. For example, we have got a sine n pi x by L as the wave function. We have to normalize the wave function to get the proper value of a, because a is after all a constant, so we need to know what the constant is. So we need to normalize it. So this is the expression of psi n within the well, and psi n is 0 outside the well. So if you look at the region within the well, the particle must be there somewhere, either at x equal to 0 or at x equal to L or somewhere in between. So again, we apply our concept of probability density, that mod psi squared dx must be equal to 1 if you integrate it from 0 to L, because the particle must be there somewhere within the well. And so you solve it, very easy integration, and you get a as root over 2 by L. So for a given system, a is a constant decided by the length of the well in one dimension. A is root over 2 by L, and so the normalized wave function is root over 2 by L sine n pi x by L. This part again is very easy. I mean, things fall into place once you know the initial logic. Okay, so this is the normalized wave function. Next, we see what are the eigenfunctions for the ones. Now that we know the normalized wave function, we see what are the eigenfunctions for the different energy levels. So for n equal to 1, this is the eigenfunction, which you can see is 0 at x equal to 0 and x equal to L. If you put x equal to 0, you get psi 1 is 0. If you put x equal to L, you get psi 1 is 0. So there are two nodes present. This is a sine function, so there will be nodes and antinodes. So clearly for the ground state eigenfunction, you have two nodes at x equal to 0 and x equal to L. For n equal to 2, this is the expression. So once again, you find nodes at x equal to 0, x equal to L by 2, x equal to L. So 3 nodes present. N equal to 3, similarly, you will see that there are 4 nodes present. So in general, we can say that at n equal to 1, number of nodes 2, n equal to 2, number of nodes 3, n equal to 3, number of nodes 4, and therefore we can safely write at n equal to n, the number of nodes will be n plus 1. So for the nth level wave function, there will be n plus 1 nodes present. So now we are at a position to draw the wave functions for the different energy levels. So at n equal to 1, this is the simplest mode, right? 2 nodes and 1 antinode. N equal to 2, next higher excited state. Next simple case, 3 nodes and 2 antinodes. N equal to 3, you have 4 nodes and 3 antinodes and so on. So this is a very, I got this diagram from the internet, and this is a very self-explanatory figure. What happens in a one-dimensional potential well? What are the forms of the function? আর এই প্রবলেমটাকে না কেউ ডিফিকাল্ট হিসেবে ভাববেই না, এই স্লাইড গুলো যদি পরপর পড়ো, you will see that this is a very very logically relevant problem, very easy to understand and very easy to remember also. Just এক্সপ্রেশনটা তো খুব সহজ, √2/l sin n pi x by l, n এর 1 2 3 4 ভ্যালু বসাও, তুমি পেয়ে যাবে এক একটা পার্টিকুলার মোডে কটা করে নোড আছে, ঠিক আছে। অর্থোগোনালিটি again, it's just a mathematical nuance that you are going to perform. Psi n eigenfunction corresponding to energy value En, psi m eigenfunction corresponding to energy value En. So this is psi nx, this is psi mx. Functions are real, there is no complex part. So m, for m not equal to n, if you take this psi m star psi n, then this is the result that you get, which is of course 0 when m not equal to n, and which is 1 when m equal to n. So the functions are orthogonal. Wave functions are they form an orthogonal set in the interval 0 to l. এটা আশা করি কারোর বুঝতে কোনো অসুবিধা নেই। ওকে, so the functions that the হ্যাঁ বলো
ম্যাম, ফিজিক্যাল ইন্টারপ্রিটেশন কি হবে?
অর্থোগোনালের ফিজিক্যাল ইন্টারপ্রিটেশন হচ্ছে, তুমি ফিরে যাও সেই ভেক্টর অ্যানালিসিস পড়েছিলাম যখন, ভেক্টর অ্যানালিসিস যখন পড়েছিলাম, ইফ ইউ রিমেম্বার, আমি বলেছিলাম যে when you have say a set of 3 vectors, if you can write them as a linear combination, then they are independent, they are dependent on each other. If you cannot write, then they are independent of each other. যদি dependent হয় তাহলে those vectors can never form the coordinate axis. যদি independent হয় তাহলে ফর্ম করতে পারে। ওকে, সো একমাত্র যদি যেমন i j k কে তুমি কোনোদিন i plus j equal to k এই ফর্মে লিখতে পারবে না, ai plus bj plus ck equal to 0 এই ফর্মে কোনোদিন লিখতে পারবে না। কেন? কারণ they form an independent set. Since they form an independent set, they form an orthogonal coordinate system. So they are independent of each other. এই অর্থোগোনালের মানেও ঠিক তাই। The different wave functions that you get for a given system are independent of each other. একজন আরেকজনকে এফেক্ট করবে না। Each energy eigen ভ্যালুর জন্য তুমি একটা পার্টিকুলার এনার্জি আইগেন ফাংশন পাবে। একটা এনার্জি মানে ধরো En এর জন্য যে psi n, সে কোনোদিনও em এর জন্য যে psi m তাকে এফেক্ট করতে পারবে না। বোঝাতে পেরেছি?
হ্যাঁ,
ওকে
yes, yes.
okay, so functions are orthogonal, which is what we want in case of a solution of Schrodinger equation. The functions must be orthogonal. Next, এটা আবার খুব ইম্পর্টেন্ট যে what is the probability of finding the particle inside the box at a particular instant? What is the location of the particle inside? মানে আমরা তো দেখলাম এইটা হচ্ছে ওয়েভ ফাংশনের ফর্ম গুলো, যে মোড অফ ভাইব্রেশন, যে তোমরা যখন এয়ার ইনস্ট্রুমেন্ট বা স্ট্রিংড ইনস্ট্রুমেন্ট পড়েছো তখন নিশ্চয়ই দেখেছো যে এগুলো ডিফারেন্ট মোডস অফ ভাইব্রেশন of the system. তো ঠিক এখানেও সেরকমই আমরা পার্টিকেলটা ডিফারেন্ট মোডস অফ ভাইব্রেশন পেলাম। এবারে পার্টিকেলটাকে পাবো কোথায়? হঠাৎ করে যদি আমি বক্সটার দিকে তাকাই, what is the chance that I can locate the particle at a particular point in space between x and x plus dx? I'll apply my concept of probability density. Px dx equal to mod psi n squared dx from definition. So in this case, you put the expression of psi x and you get this expression 2/l sin square n pi x by l dx. Okay, probability density. কখন maximum হবে? Sin square function. So this will be maximum when this argument n pi x by l is equal to either pi by 2 or 3 pi by 2 or 5 pi by 2, etc. That is odd multiple of pi by 2. So this is possible at the positions of x equal to L by 2n, 3L by 2n, 5L by 2n, that is odd multiples of L by 2n. So ground state n equal to 1, therefore probability is maximum at, see from here, x equal to L by 2. First excited state n equal to 2, probability is maximum at L by 4 and 3L by 4. Then for n equal to 3, px is maximum at এখানটা থেকে দেখে নাও L by 6, 3L by 6, that is L by 2, and 5L by 6. And so on. So this is the probability density expression. Ground state, it is the highest probability of locating the particle is in the middle. It's almost, if you take the probabilistic chance, then the highest probability of locating the particle is at L by 2. That is the middle of the box. If you go to the next excited state, the first excited state, then there are two peaks. So you can locate the particle with the highest probability either at L equal to 4 or at L equal to 3 by 4. In the next state, there are three positions at which there is chance of finding the particle with highest probability. L equal to 6, sorry, x equal to L by 6, x equal to L by 2, x equal to 5L by 6. So again, just from the expression of the wave function and by putting the different values of n, you very clearly get the probability densities of the particle in the different energy states, ground state as well as any higher energy state. Okay, these are the probability densities. This picture, again, I have taken this comparative picture from the internet, but again this gives you a comprehensive understanding of the problem that we have been discussing so far. The different energy levels, ground state, first excited state, second excited state, and so on, and the energy values are also given here. The wave function, that is the mode of vibration corresponding to the different energy levels. First, ground state, only one mode, 2 nodes and 1 antinode. Second state, 3 nodes, 2 antinodes. Third state, 4 nodes, 3 antinodes, and so on. And the corresponding probability densities. Ground state, you can locate the particle with highest probability in the middle. First excited state, there are two positions at which you can get the particle with highest probability. Second excited states, 3 positions with where you can get the particle with highest probability, and so on. Okay, so this diagram gives you a very comprehensive understanding of the problem. If you logically, as I told you, if you logically go through the sequences and then you arrive at this diagram, there should be no problem for you to attempt this at any level. Okay. We can also get the momentum eigenvalue since we have considered non-relativistic motion. So En equal to Pn square by 2m, the total kinetic energy, since the particle is moving, and we can easily, putting the value of En, we can easily get the eigenvalues of momentum in terms of the quantum number n. Okay, so Pn can be plus or minus nh n pi h cut by L, that is nh by 2L, if you put the value of h cut as h by 2 by. So these are the momentum eigenvalues, nh by 2L. You can see that momentum eigenvalues are also discrete, but the difference between between two consecutive momentum values is constant. In case of energy, we saw that the difference increases as you go to higher levels. In case of momentum, they are equispaced. If you draw momentum levels, then you will see that they are equispaced. the difference between any two consecutive levels being h by 2l, which is a constant. Okay. Plus or minus sign before the momentum eigenvalue, what does it indicate? It signifies the fact that the particle can either move in the positive x direction or in the negative x direction. That is, it is performing back and to and fro motion within the box. Okay, that is why plus and minus. Now comes 0 point energy. This is very important, and please don't Google your answers. If you do Google your answers, then you must also know which answer to choose. Alright, আমার মেয়ে যখন history project করতে বসে and she asked me that effect of Renaissance, when I googled, I got so many results. Which one should I take? Which one should I write? I tell her I don't know, because I have not studied history after class 10. So I don't know which is right and which is wrong. You go back to your textbook, refer to your textbook, see which is correct, which matches with the information given in your textbook, and then take that information. Because when I Google, if someone says, if one website says that Michelangelo drew this and this in this and this year on Sistine Chapel, I don't know whether it is wrong or right. Precisely because I have not read history in that depth. So similarly, if you are Googling your answer, then you must also know whether you are Googling the correct, whether you are, when you write a certain phrase on the search box in the internet, you get a plethora of answers, out of which it is your task to fish out the correct answer. And how will you fish out the correct answer if you don't have the concept? Okay. So when you are fishing out your responses from the internet, then please be sure to match it with a book or a note that the teacher has given. I don't know, the kind of answers I've got from ground state, I was on the verge of forgetting what a ground state is, what 0 point energy is. Okay. Anyway, so 0 point energy, why? We know that the ground state is the lowest possible energy. And in this particular case, we have seen that this lowest possible energy is non-zero, which means that the particle is never at rest. Although it is at the ground state, but still it is never at rest. And this is in agreement with Heisenberg's uncertainty principle. Why? Because the particle is trapped within a finite region in space, right? So the uncertainty position is fixed. It is the length of the well. Uncertainty in position is L. That much information about its position is available, right? Delta x is L. So if you know the position, you can no longer know the momentum with conformation. And if the particle is at rest,
Oh.